Bounded above means that you are going to get to one y value that you can't pass. For example, you are going to have a maximum y value. The most common type of bounded above that you guys have seen so far is definitely upside down parabolas or upside down absolute values. It just depends on what happens, but basically none of your graph is going to go past this y value. Okay, likewise, bounded below just means that you're going to have one y value that you can't get past, and that's basically going to look like a maximum. Alright. Oops, I said maximum. I meant to say minimum. So again, the ones that you guys are most familiar with, again, are parabolas that go straight up and down. There's going to be some certain y value that you are never going to be able to get past, like parabolas are never going to come back down and be like swoosh for funsies. Or absolute value signs. Again, absolute value graphs should be there as well. Alright, and what does it mean by bounded? Well, that means that you guys are actually going to have two y values that you can't pass. Alright, and basically that means that it is going to be bounded above and below. And the most common graph that we are going to be taking a look at this year is that we are going to have our axes. And it's going to be an x and a y graph. And there's going to be some graph that looks like that, where basically you guys are going to have maximums along this particular value, and you guys are going to have minimums along that value. Alright. Bounded on an interval is a heck of a lot less common. That just means that you have a restricted domain. And that's basically it. It's a restricted domain. And it'll give you guys that, or it'll tell you that if it's bounded on an interval. So something like 0 is less than x, which is less than or equal to 3. So you guys would only have to graph this piece of graph if I had for example, again, x. So again, this is the most common with piecewise functions. So I would just have to graph from 0 to 3, and it would just look like this little line segment, that's it. Again, it would have to give you that, and technically, yeah, it would not actually be at 0, so you'd have to say that that's a whole. But anyways, technicalities right now aren't that important. Extrema. So, extrema are just your maximums and minimums. That's all it's a fancy thing for. And there are two different types of extrema. There are local extrema, which are just the lowest and highest points in a section of graph. Alright, Alright, so let's say that I had a graph that looks something like, again, this, and I just wanted the local extrema for this piece of graph. Well, my local extrema for this piece of graph, well, I've got a maximum here, and that's about it. Other than that, my minimum value would be way over here at the end of my graph if I'm just looking at that little section. Alright, absolute extrema is the most high and most low point total on your graph. Alright, so again, local extrema were the lowest and highest points in a, I should have said in a section. Oh, graph, and then the absolute extrema are the most high and the lowest points total on my graph. So if I'm not looking at this little section, sorry, I can't get rid of that little point, but if I look at this whole thing, I see that my absolute maximum, my highest point on that graph should be at this particular point, and then my actual lowest point would just be right here. So that would be my absolute minimum total. Alright. Symmetry, there's two different types of symmetry that we are going to talk about. What you guys have talked about so far is that symmetry probably looks like you can draw a dashy line straight up and down and fold it, and it would be the same on both sides of that sheet of paper if you were to actually draw it out and fold it. So looking the same on left and right. Or up and down. There's actually two different types of symmetry that we're really going to be talking about going forward. That is symmetry about the y-axis, and there is symmetric about the origin. So symmetric about the y-axis, again, most commonly, you guys will see, you got an x and a y-axis, you've got some parabola looking thing. Alright, then let's make it nicer. So we've got some parabola looking thing, and it literally looks like this could be folded along my y-axis, and it would be the same thing on the left and my right. Versus symmetric about the origin. What's going to happen is I'm going to have some graph, and it's going to look like, okay, I've got this piece here. Well, if I turn it around about the origin 180 degrees, just flipping this around, I would get some graph over here that looks like that. So those are the translations. Flipping it 180 degrees. Alright. Even function just basically means that you have a y is equal to x to the n, and n is positive, and, well, not even necessarily positive, but n is even. Alright, likewise, if I have an odd function, it's going to be y is equal to n to the x, or x to the n, it doesn't really matter. In this case, n would be odd. Okay, and that's the one that are. Alright, so even functions typically are symmetric about that y-axis, even if it's not exactly on the y-axis. And odd functions are going to be those symmetric about the origin. But again, we'll talk about those later. I'm not too worried about this kind of stuff yet, but we're going to get into it. So I thought I'd show you guys a little short, quick examples. That way everybody's a little bit familiar with it. Alright, vertical asymptotes are just those x equals some number. Okay, and horizontal asymptotes are just going to be some y equals number. Again, vertical asymptotes are the ones that go straight up and down. Horizontal asymptotes are the one that goes side to side. Alright. End behavior is just literally what's happening at the end of my graph. And this is broken into 4 different bits. What is happening at the end of my graph? So we're going to talk about what's happening going to the left, going to the right, what's happening as we go up, and what happens as we go down. We're going to be talking about all 4 of these things when I talk about end behavior, because you have 4 different sides on your graph and on your pieces of paper. Okay, little tiny table, which apparently I needed 1 more box for, but that's okay. I'll live with it. Alright, so we've got this whole thing, and I'm like, okay, well what if I've got some ax to the m over bx to the n? Well, in my first case, I'm going to take a look at what if m is equal to n. Okay, so in this case, what's going to happen is that I would have something like 3x to the 4th over 5x to the 4th. What's going to happen is my x's would cancel out because I've got the same thing up top as I do on the bottom, being left with just the numbers in this case, which would be 3/5. In general form, though, that would just leave me with a over b. Alright. And in this case, I would have just a horizontal asymptote at y equals a over b. Because again, horizontal asymptote should be y equals. Alright, the next one I'm going to take a look at, my end behavior model is going to be the same thing. A times x to the m over b times x to the n. Alright, but this time I want to take a look at what if m is less than n. So, what's going to end up happening is that n is bigger, so that would be like 3x to the 2nd over 5x to the 9th. And what's ending up happening is we would actually have 3 over 5. I have 7 more x's on bottom than I do up top, so I would end up with 3 over 5x to the 7th, because 2 of my x's would cancel out, leaving me with 7 x's on bottom. So in general, what happens, I would have a over bx to the n minus m on bottom. And what's going to happen is I'm going to have a horizontal asymptote at y equals 0. Because as I plug in bigger and bigger and bigger numbers for x, my denominator becomes increasingly large, which is going to make my actual number in general very, very small. So it is going to approach 0, but never actually touch 0. And finally, that last thing that we're going to take a look at is this end behavior model of that a times x to the m over b times x to the n. And this time I'm going to take a look at what if m is larger than n. Alright, so what if I had 3 to the x to the 9th over 5x cubed. Alright, so again, this time I see that, okay, well, 3 of my x's are going to cancel out. on top and bottom, but I'm still going to have 6 x's stuck up here, so that would actually simplify to being 3x to the 6th over 5. Alright. So now in more simplistic versions, or in general form, I would have now a to the x to the m minus n this time, all over b. Alright, because again, I ended up with more x's up top, so it makes sense that I started off with my top number minus my bottom number, because that's ending up what happens. Alright, so because of this, I'm going to have my x's up top, so as I'm plugging in bigger and bigger and bigger numbers for x, what's going to happen is my numerator outgrows my denominator, meaning that I'm not going to approach just one number this time. So this time I'm not actually going to have a horizontal asymptote. And what's ending up going to happen is I'm going to have something that we're going to talk about this year called slant asymptotes. And with that, have a great rest of your day. I'll see you tomorrow.